Okay, so welcome everybody back to our 3D geometry and vision seminar series. And today we're very excited to have Gerard Pons-Moll speak about generalized neural implicits and humans interacting in the 3D world. We also have two guest panelists, Lourdes Agapito and Siyu Tang. So anybody who's watching live, also feel free to ask questions in the chat and we'll get to them at the end of the talk. So Gerard is a professor of computer science at the University of Tübingen, and he leads the Real Virtual Humans research group. His research is lying at this very interesting intersection of computer vision, graphics, and machine learning, focusing on analyzing people and videos and creating virtual human models. So his research has been at the cutting edge of statistical human body modeling in terms of pose, in terms of shape, in terms of clothing, and has been widely used in both industry and research. So of course, his work has also been recognized by many awards, including an Emmy Noether Grant, Google Faculty Research Award, Facebook Reality Labs Award, and recently the German Pattern Recognition Award. And so we're very excited to hear Gerard today.
Yeah, thank you, Angela, for inviting me, and thank you again for organizing this super cool workshop or seminar series. I think it's really nice. Yeah, thank you for being here, also the panelists. And yeah, so basically, I just want to warn you, this talk is more about neural implicits than it is about humans interacting in the 3D world. But I chose this title because I want to maybe at the end discuss how these two areas of research can come closer together. So since the beginning of civilization, we spent our lives interacting with other humans. And that's why humans have been central, and they are central to our lives. This can be seen, for example, in art history, where the human has been depicted multiple times. Now, in the era of AI, it's not surprising that there's a lot of interest in building agents that look and also behave like real humans. So here, we would like to build an agent that is capable of navigating the 3D world and interacting with the 3D world. Like, for example, performing complex activities like picking up a book from a bookshelf and finding its way through the 3D world environment. This is a video from our recent paper, which we call it HPS, which comes from Human Positioning System. And here it was our attempt of capturing the first data set where we see humans interacting in large 3D scenes. And our hope is that the community will jump on this data set to build models of humans interacting in the 3D world in a way that they behave like real humans. Okay, but to build such agents, these agents need some more basic capabilities, right? This is an extremely complex problem. So one component, for sure, they need to turn visual data. This might be an image or a pair of images. They need to turn it into a 3D representation. And in the simplest form, this means a surface that is smooth, it's renderable, and it's complete. Now, this input might not always be just a single image. If you were considering a robot, for example, like the input could be depth sensors, or the input could come from 3D scanners, or it could be the output of another computer vision algorithm, right? So the input could be, for example, sparse voxels or dense voxels, or it could also be partial point clouds. I'm just gonna minimize this window. Yeah. Yeah, so the goal is then to obtain a surface that is complete from this input that is typically noisy or it's incomplete. So when we look at the literature, we find different kind of representations. So one is, for example, voxels, which are amenable for 3D convolutions. This is an advantage, but then you have these blocky artifacts because you need to discretize the space, and they are also memory intensive. Points are also a representation that people have used, and it's quite flexible, especially in terms of representing different topologies. However, the problem with points is that they are not straightforward to render, and basically you end up with shapes that look like what you see here. Meshes are also a representation that has been widely used, maybe the most widely used representation, but then you have triangulation artifacts, and more importantly, you have problems with dealing with different topologies. It's difficult to turn meshes into different topologies. Now, since 2019, there's been a sort of revolution of implicit functions used within deep learning contexts. And the idea is to classify the space into inside the surface and outside the surface. And the advantage of this is that it's continuous. And another advantage is that basically you can represent many different topologies. Okay, so most of you people attending in this seminar know already what an implicit function is, but just to refresh some ideas, an implicit function is basically like you need to define a function f that takes every point p in the 3D space and classifies it as being inside, shown here in red, or being outside, shown here in blue. And now the surface, right? So this is a division of the 3D space. And the surface are such points P that are at the boundary between inside and outside. And if you have this 0, 1 representation, this would be the points that take value f of P equals to tau being 0.5 in this case, right? So the surface in this case would be this blue, dark blue line. Now, why is this representation particularly interesting? Well, because if you have a topology change, if we were using meshes, we would need to track which vertices are connected to which other vertices. And this is difficult to do. And more importantly, it's very difficult to differentiate through. In contrast with an implicit function, all we need to do is to change this f of p, and we will end up with two different separated surfaces. And that's no problem. We just need to track the changes of f of p and don't worry about connectivity issues. So this is a huge advantage, I would say. Now, how is this used within the context of learning and representation learning of shapes? So there were 3 papers that came at the same time at CVPR 19 that came up with almost the same idea. And it's a super simple idea, but a very powerful one. So the idea is to classify every point in the 3D space as being inside or outside for a given shape. As simple as that. Typically, we are not interested in memorizing a shape using a neural network. Therefore, we typically have to condition the input of the neural network on the actual shape we are studying. For example, the input might come from, as I said before, some noisy observation. This might be a sparse point cloud or a partial point cloud or low resolution voxels, which are denoted here as X, capital X. Then you get like latent code. This lies in some n-dimensional space, and then you decode this into 0, 1, right? And then you can do this for many points, as many as you want at test time. And once you have lots of points being classified as inside, outside, you can run marching cubes, which is a classical computer graphics algorithm to reconstruct the surface given these occupancy maps. Okay, so good news is that this is continuous. It can represent multiple topologies, and it's quite smooth, and you can choose the resolution at test time. So these are all really good things. The bad things are we tried this for representing articulated objects like humans, for example, and we run into some problems. So for example, here, this is the input X, and you can all see that this is a human sitting on a chair. That's because we have these mental models of how humans look like. And the networks are not capable of reconstructing these smooth surfaces. So it basically misses the limbs. And yeah, the results are not very accurate, especially with articulation. So why is that? We wanted to dig deeper into what are the causes of these artifacts and problems. So the first problem is that we are encoding the input into a latent code that lives in some n-dimensional space. But we lost the connection with the original 3D space in which the data lies, which is the 3-dimensional space, right? So Z and R3 have no connection anymore. So this is the first problem. And the second problem is that we're sending point coordinates to the decoder. And point coordinates alone don't carry any information about the shape, because I can transform, I can rotate the shape, or I can displace it, and the coordinates will change, but the intrinsic shape will not change. Therefore, this design choice of sending points to the decoder is maybe not the best one, I would say, right? Because it will not have built-in invariances that we typically are interested in. So how can we change this? So this is what we addressed in CVPR 2020. This is actually last year, but it feels like ages ago already. So how do we deal with this problem? So the first thing is, well, we do 3D convolutions on the input, and like this, we obtain a multi-scale grid of deep features. These are these cubes here represent multi-scale grid of deep features. And these deep features go from more detailed to more global representation. So the smaller the cube, deeper, it means more global, and the more superficial, it means more focusing on local details. And now, instead of sending the point to the network to classify it as inside or outside, we're going to extract deep features at these continuous locations in this multi-scale grid. And we're going to obtain these deep features, which are centered at the point, and they will contain global and local information. Fn of P, more global, until F1 of P, more local. And then we're going to send these deep features and classify this point as being inside or outside. Now, very simple change, very simple idea, but again, very powerful. And as you will see in our experience, this leads to significant improvements, and it's very effective. So mathematically, what did we do? We had this basically state-of-the-art models that were taking some latent code Z and the point P and classifying it as 0, 1. And now we're replacing the Z with this multi-scale grid of deep features. And recall that these are cubes, so they are aligned with the 3D space. So we didn't lose this connection. And, oops, sorry. And the second thing we did is extract deep features at these continuous locations at F1 until Fn, and then classifying as 0, 1. And yeah, we use this for a variety of task completion tasks. For example, super resolving voxels at low resolution or at a bit higher resolution. And notice that the input is like this blocky voxels and the output is a smooth surface. And we also used it to complete what would be point clouds coming from a depth input, right? And you can see that wherever you have data and details, it retains the details. Wherever you don't have details, it produces a smooth surface that is quite reasonable. Okay, so we compare to these other models, and yeah, I mean, across all shapes, it was producing more details and better completions. And this is especially true for articulated shapes. But also in general objects and ShapeNet, it was at that time the state of the art. I'm not sure what happened in the last year, but it's still very powerful and we use it all the time. Okay, so I mean, the numbers you can check in the paper. I don't have time for this now. But we used it for 2 challenges at CVPR 20 and ECCV. Oh, wait, no, at ECCV 20 and CVPR 21, there's a challenge organized by University of Luxembourg, which is called the SHARP challenge. And basically there you have to reconstruct scans and complete the texture and the shape. And the 2 times, the IFNets was the best performing method. And yeah, so this is like maybe some evidence that this is actually a simple idea that is powerful. And I also encourage you to participate in this workshop. It's a lot of fun, and the award for the student is quite high, actually. Yeah, so these are some other examples. So notice that it can reason about local and global shape structure. Okay, so but to train these models, we needed very clean data, which was surfaces that separate the space into inside and outside. But we don't always have this, right? So for example, when we consider, for example, a garment, it's an open surface. We cannot define what is inside and outside. Or we have a 3D scan of a room, it's also not clear what is inside and outside. And for this, we need to change not the input representation, which is what we changed until now, but we also need to change the output representation. And this is because like all these kind of shapes, what I was describing before, open surfaces and manifolds and complex shapes with inner structures cannot be represented with these SDF and occupancy-based models. So surfaces that do not divide the space into two regions cannot be represented, and we need a different output representation. So our solution is again super simple, but it's also very effective. So what we do is, instead of predicting the signed distance, we predict the unsigned distance with a neural network. Now, people had used unsigned distances for other tasks, like, for example, to process 3D scan data, but they had not been used in this context of neural implicits. So what do? We take the unsigned distance, which is predicted using the input of the IFNet. This is the same, the multi-scale grid of deep features. And now we're going to predict for every point P, the closest point, the distance to the closest point to the surface, which is Q, okay? And like this, we can represent a wide variety of shapes. Okay, just to simplify notations, I will replace this big notation of multi-scale grid of deep features, and I will just refer to f of P. But bear in mind that we're not sending the point coordinates, but we're doing this deep feature thing before decoding. Okay, but not so fast, because how do we reconstruct the surface? Remember that to reconstruct the surface, we need to run marching cubes, and marching cubes requires to classify the points as being inside or outside. And with an unsigned distance, you don't have this. So we need something else. So imagine this is the point cloud X, and we want to reconstruct the white surface, right, which is the bus with inner structures. So what we can do is, because we have a neural distance field, we can easily compute the gradient, and the gradient field is represented with these red arrows. And this is the spatial gradient, not the gradient with respect to the neural network parameters, but the gradient with respect to P. But we can also do this by backpropagation. And okay, so one idea would be to follow the inverse gradient direction until I land on this zero level set. Might be one idea, but we actually can do better than this. What this equation tells us is that we can take P and we can subtract in the gradient direction f of P, which is the distance, units to land on the surface. So this is what this equation is telling us. And so it means that in one shot, we can project a point back to the surface. And now why is that? If you look at this equation, f of P equals the minimum over Q. If you take the gradient, I mean, mathematically, it will for sure point to the closest point, right? And basically, this is in the direction of the closest point. And now, how much units of distance do I need to move in this direction? Well, this is given by the distance itself. That's why it's a distance field. So you just need to move f of P units of distance to land on Q. Now, this is really nice theoretically. In practice, and almost no one used this, although this was known in computer graphics, but we barely found any paper using this. But it's a powerful thing. Now, this is the theoretical result, but in practice, we need to, because the distance field is not the theoretical one, it's a practical one. We need to project using this equation 3 or 4 times until the point is really spot on the zero level set. Okay, so using this, what we can do, what we could not do before, is that we can reconstruct the inner structures, like for example, this chair inside of the car. And so basically we can reconstruct all these inner structures. We can also reconstruct surfaces that are open, like garments that are open. And this is quite useful for a number of problems. We can also use it to complete full 3D scenes. And yeah, we don't need watertight meshes. We don't need clean data. We can just train with raw scans, which is also different from what was the state of the art at that time. You just take the raw scans, compute like the distance fields and train from that, and then you can complete a test time by projecting these points to the distance field. So this is also quite nice. And yeah, I'm not going to get into detail, but in the paper, we also show how to render depth directly or normals using a variant of sphere marching. Yeah, we have a comparison for the ones of you who are into this topic. You might know the paper SAL, which is called Signed Agnostic Learning, or well, I forgot exactly what it is, but it was very similar to our approach. The main difference is that they basically require, they still output a signed distance field. So they can train from raw scans, that's a good thing, but they cannot output open manifolds. And yeah, I mean, that means that in the end, we end up performing quite better, especially for shapes that have inner structures. Yeah, check the numbers at the, this is at the supplementary material of this NeurIPS paper. Okay, but we realized that this is even more general. We started with a computer graphics, computer vision algorithm, but we realized that this can be used more generally for general regression. So I can use neural distance fields to basically complete general functions like linear, quadratic, sinusoids, or spirals, and complex manifolds. Now you might think, well, I'm really not impressed by this because I can train a neural network to do the same thing like with standard regression, and yeah, I'm not impressed. Well, that's true, but notice that manifolds that are multimodal, and multimodal, I mean that for a given x, take 0 here, you have multiple y values. If you train a general regressor, what's going to happen is that it's going to land right in the middle. It's going to average the different outputs, right? And this is not typically what you want. You want to put density wherever you have data and put 0 density when you don't have data. So how do we model this regression with distance fields? Well, you typically have this regression problem, y as a function of h and the dependent variables. And we can formulate this as a function f that for the points where you have data, x1, xn, and y, in this case, y given by this function h in explicit form equals 0. Okay, so that's how we represent this implicitly. And now, like, we're gonna do like this computer graphics technique, which is sphere marching on these like basically general functions. And we're gonna move along the ray, like the ray shown here in the rightmost square, until we intersect with the unsigned distance field. And like this, we can obtain regression that works for not only functions, simple functions like linear or quadratic, but also for spirals and more complex manifolds. Yeah, so this is something that we are also interested to continue exploring how far we can get with these neural distance fields and what connections are there with also energy-based models in machine learning. Okay, so to give a bit of summary, comparing what are parametric meshes and implicit functions, I would say this table summarizes it a little bit. So the meshes are good for control, and basically they are lightweight, and they also have a very, yeah, they are easy to grasp and to manipulate. However, it's difficult to generate different topologies, and it's also difficult to generate details. And the implicit functions are not immediately controllable, although at the end of the talk, I'm going to talk about a model that is to control implicit functions, and they are good for different topologies and good for details. And also they seem to be very, this idea of classifying every point independently seems to be very compatible with neural models. Okay, so let me now jump into a project in which we sort of combine a little bit of this implicit representation and a mesh-based representation. And this is what we call LoopREC. And LoopREC is designed to obtain registration, which is registering a template human mesh into a given 3D scan. And for the ones of you who are not familiar with human modeling or shape modeling, registration is the workhorse of most models. The reason that simple is so good is because the registration is very good, right? And that's the case. So if you have good registration, you're going to build a good statistical model of bodies or faces or hands or whatever you have. So it's a really important problem. So how is this done traditionally? You usually use like what is called a iterative closest point, which is some sort of EM algorithm. You first obtain landmarks. So again, the objective here is to register this template shape shown here as a T-pose to a given 3D scan. And this is because you want to bring the scans into correspondence. You want to know for every point, what is the nose, what is the eyes, and what is the head. So you will obtain landmarks, as you can see here in colors. And this is obtained with some key point detector or whatever, or finding closest point or a pre-trained network, your favorite landmark detector. And then basically you're gonna, after finding these correspondences, you're gonna minimize the distance from the scan points and the model points after transformation. So you're gonna sum over the correspondences between scan points S and model points M, the distance from the scan point Si to the transformed model point Mj, and transformed by a function M. In this case, this could be the simple function or morphable model, whatever model that you have that takes points in an untransformed space and it transforms them with some parametric function, okay? So that's what you typically minimize. And then you iterate between finding correspondences, deforming the model, finding correspondences, and so on. Now, the problems with this is that this is instance specific. You need to do this for every instance, and there's no reasoning about a shape collection together. It's prone to local minima, and it's also not end-to-end differentiable. Finding the correspondences and then optimizing needs to be iterated. It's not end-to-end differentiable. So how can we train these end-to-end and leverage this idea of like having a shape collection so that the network learns to produce correspondences while we're doing the registration at the same time? Because this would be very appealing. So what we do here is we want to learn a function f of phi that maps every scan point to a model point in a continuous manner, right? And then if we have this backward function, right, we could take this model point M and forward it back to the scan to close this loop. And this loop would create what is called a self-supervision loop and would allow us to train directly from raw scans without having to label what is a nose and what is an eye. Again, the questions and the key challenges here is how can we train the network f of phi and optimize the model parameters? The model parameters are denoted as X here. This might be the pose, the shape, the clothing, whatever you have, right? And how do you ensure that the correspondence predictions lie on the model surface? Because f of phi might produce points that lie off the surface, outside of the surface. So how do you put these hard constraints in the learning framework? Not so easy to do. And how do you integrate this correspondence prediction with model fitting? So let's look at the first problem, this off-manifold correspondences. Oh yeah, so how do we reformulate this classical problem? So we have now, over a collection of scans, X, which is mathcal X, we're summing over scans from J1 to N. This is the N scans that I have in my collection. And then for every scan point, right, I want to minimize the distance between the scan point and the transformed model point MK, okay? And for this, I need to find the model parameters XJ as well. Now, how do I bring these neural correspondences in the equation? I can replace the model points M by the predictions of the neural network, okay? So the network takes a scan, predicts the model point, and now I use the morphable model to close the loop. Okay, this seems all very intuitive, seems like a good idea. Now the problem is, how do I train f of phi such that always lands on the manifold in the canonical space? Well, one option might be using a UV map. You learn first to predict the UV coordinates. By the way, a UV map is an unwarping of the 3D surface into 2D, such that you have a one-to-one correspondence between the 3D point of the surface embedded in 3D space and the surface embedded in this 2D plane, okay? And so we can predict with the f of phi, we can predict the UV coordinate, and then we can basically, using the forward map, we can obtain like this 3D correspondence. Okay, this would do the trick. It would land always on the surface, but the boundary is not differentiable. You need to cut the surface to create a UV map. You have distortions in a UV map inevitably. And also, like, this is like, who likes UV maps anyways? So I think like a lot of people are quite annoyed by UV maps because you need to design them or cut them, like automatic algorithms. They always have some problems. And yeah, it's kind of annoying. So how can we get rid of these UV maps and have something more, perhaps more elegant? So again, the problem is that we might land off manifold, right? And off manifold, I don't have my morphable model defined. I don't know what to do. I don't know how to transform these points, right? So this is M, for example, take simple. Simple is only defined for the vertices, nowhere else, okay? So it's not defined off the manifold. So what do we do here? So what we can do is, and this relates to my previous explanation of neural distance fields, is we can compute a distance transform. So here what you see is that every point in space encodes a distance to the closest point. And also I'm coloring like the closest point with the same color. So that's why you see this kind of divisions, right? So for example, here you have green because the closest point is this left leg and so on, okay? So this is basically using the distance transform, we can diffuse the model beyond the surface, right? We can propagate this function that is only defined on the vertices to all the 3D space. This is good because now we have an equivalent function G, which is not defined on the vertices, but is defined on all the space, which is this 3D space, okay, this canonical space. But that's great because now, at least if my network predicts off the manifold, I know how to forward map this point. Okay, so at least I'm not clueless. But still, I don't want to keep predicting points further and further away from the surface, right? That's not what I want. So I can add a constraint, which is a Lagrangian constraint, to force the predictions to lie on the manifold. So what am I going to require? I'm going to require that the model point f phi of s, this is the prediction of the neural network, should evaluate the distance, should evaluate to 0, because then it means it's on the manifold. So basically I need this L surface. This is a constraint that says I want the distance to be as small as possible. And that's it. So now how does this look like? We have this model point predicted by the neural network f of phi. And now, like, we replaced by G. So now it's defined if my network decides to predict off the manifold. So that's good. And also I need to add this Lagrangian constraint to make the predictions M, right, f phi of S, as close as possible to the surface. And now we have an equation that we can basically optimize with respect to the neural network parameters phi and the model parameters, parametric model parameters xj for every instance. And you can optimize this end-to-end and learn to predict correspondences and at the same time obtain the registration, which is quite nice, I think. And this equation allows you to train in an unsupervised manner, theoretically. In practice, that's not what happens. If you just plug this into your optimizer and you just try to learn everything, you fail. And that's what happened to us. I was also not very surprised by this because there's still lots of local minima. And if you start predicting wrong correspondences and optimizing wrongly, and then everything like doesn't converge. So you need a little bit of warm start. And here we used 1,000 scans to train a supervised model to warm start the correspondence predictor. And then once you have the warm start, you can add more and more unsupervised data. So what you're seeing here is in the rows, you see two metrics, vertex to vertex. This measures alignment quality, and scan to scan This measures also alignment quality, but it doesn't care about whether you're really accurate along the surface. And every column shows the percentage of unsupervised, additional unsupervised data that we used. So ideally, you want this error, the more unsupervised data, to go down. And this is what we are observing. We start from 9.3 centimeters at the beginning with only supervised data, and then like this goes down to 1.5 centimeters. This is like the vertex to vertex metric, which is quite demanding. The scan to scan metric goes down to 4.2 millimeters. That's typical. Vertex to vertex is always much higher. Yeah, so we compare to other models, especially models that don't use a parametric model as the forward model. They just learn everything to deform the vertices and so on. This is called 3D coded. And yeah, we perform significantly better. And that's because the parametric model also produces really useful constraints. It knows how a human body should look like. Okay. How are we doing on time? Just because now I'm more or less at, I cannot see my clock because I'm not in presenter mode.
Like still 10 minutes or so.
Okay, cool. Okay, so what this means is that now we had some sort of best of both worlds. We use these implicit functions to train a correspondence predictor, but we still had this parametric model with the meshes, right? And so you could see LoopREC as a combination of implicit and mesh-based representation. Okay, so look at this table, and I'm showing here control and meaning. Like I'm flagging implicit functions as bad, no control. This slide I did last year, and I think things are changing now. And this is what I want to present now, which is called neural GIF, neural generalized implicit functions for animating people in clothing. This is an ICCV paper. And the goal here is to take some input pose, the skeleton that you see here, and produce a 3D shape, including clothing and details, such that you can control it as a function of pose. And also, we want to train from raw scans without needing registration. This will have some advantages and some disadvantages, but in principle, not having to do registration, all these steps that I explained you with LoopREC, seems also appealing, right? We will lose something, of course. We will not know where the eyes are at every instance of time, which is a bad thing, but we will allow to produce a surface that is renderable, and this is quite appealing. So what is a generalized implicit function? So let me like fix some ideas here. And these ideas, actually, we borrowed the name from this paper from Sklarov and Penland, where they present the generalized implicit functions. Really nice paper, only 4 pages, really to the point, and really nice. And when we were doing this project, I realized, oh, actually, I remember some paper that was doing something very similar. And actually, yes, and this is a paper from 91. So for those of you young students who don't read papers before 2017 or something, bear in mind that sometimes really cool ideas can come back, right, with more modern methods. And this is one example of this. So, okay, what is a generalized implicit function? So imagine now I have this implicit function that I had before, this surface, and I want to rotate it and translate it. How can I do this? So I take every point P, right? And I want to rotate it and translate it and still keep the sign distance or the occupancy, whatever I had, right? So if I had a surface S represented as P and F of P, right? F of P taking this, like representing the surface as the points and the boundary. Now, if I want the rotated and translated version, all I need to do is a change of variables. I need to take, I need to consider the points P prime, which are in the transform space, right? And now, how can I find the points that are at the boundary? Well, I can do the following trick. I can replace here what goes inside, right? And replace by R minus 1, P prime minus T. What does this mean intuitively? It means I'm taking a point, this one, right? For example, can you see my cursor?
Yep, we can see it.
You can see it. So take this point, for example, and I want to know if it's inside or outside. So what I can do is, like, I can bring it back. Let me find it, actually. Bring it back to the original space, right? And evaluate this distance field or this occupancy field in this original space. And this is what this equation is telling you. Now I'm going to have the surface in the post space P prime, right? As all the points that satisfy this equation, right? F of R1, R minus 1, P prime minus T equals to this boundary value, right? Simple enough, but this allows you to deform many different shapes and create many different shapes as deformations of one another. This is just rigid, but you can generalize this to more general displacement fields. So you can apply a displacement field to deform this shape. And this doesn't work like the same way as displacing a mesh. It works the reverse, right? When you displace a mesh, if the displacement field goes outside, the mesh grows. With implicit functions, you have to think backwards. If you apply a displacement field outwards, it means that the shape is reducing, okay, because it goes in the other direction. Okay, so now we have the surface S of S prime as the point that satisfies the equation P prime minus F of P prime minus D, and D varies along X, Y, Z, right? Equals to this boundary point. Okay, and like this, we can deform the shape, we can stretch it, we can change the parts, and we can do many things. We are broadening the class of shapes that we can represent. We started exploiting this idea a little bit, but we didn't get to the full bottom. This is like a collaboration I did with Google. And there, what we did is like a function, an implicit function for post-human. So basically, you have an input, which is a pose, and you can produce a surface at the output. And we use this trick of taking the point and unposing it and evaluating the occupancy on this unposed space. Now, but we didn't add this other more general, this deformation field on top, and that's why the model is good, but it's not very detailed, and also it didn't exploit enough of how humans look like. It didn't exploit the simple model. Now there's new work coming at CVPR, which was actually concurrent to what we were doing. These are works Leap actually and Scannimate. I think CU was involved in both. And they continue on this idea, and they also leverage more the simple model. But I'm going to explain how this work is different to neural GIF. Yeah, so you can think of these models as a sort of simple model that outputs signed distance function as a function of pose, right? And having the signed distance again is useful for different topologies, for complex clothing. If you want to deal with interactions with environment, you have already the distance field. For example, I want to know how far my hand is from the glass, then I already have this with my model. It's really useful, right? So we built on this neural GIF idea and on this generalized implicit functions idea. So what we're going to do is I want to know the occupancy of a given point P for a given pose, right? And I want to produce, let's say, a cloth human, right? This is the output on the right side. I want to cloth this person in a given pose, right? So what I'm going to do is consider these query points, map them to the canonical space. So I'm going to have a neural network that predicts the blend weights for this point, the blend weights of a standard skinning, okay? So this is given by this equation. This is sum of I from 1 to k and wi's that combine rigid parts. So for the ones of you who do not know what I'm talking about, is basically blend weights are linearly combining the rotations of one part and another part to find how a point in the middle actually deforms, okay? So this is given by this equation, and what the network predicts are the blend weights themselves, not the point directly, but the blend weights. And then we are applying the inverse transformation. Remember, from this easier example, we need to apply the inverse transformation. And yeah, these BIs are basically the rigid parts. Now, we're not done yet. We also want to model the formation of clothing, for example, that is dependent on the pose, for example, like wrinkles, folding, and things that are highly dynamic and non-rigid. So that's not a problem, because we can also apply learn a displacement field that varies along XYZ in this canonical space. And we can apply this to the points, right? And after doing these inverse transformations, I can evaluate a learned signed distance field that produces the signed distance. And now here's the thing that you have to think, like remember we started off with the post space. So all I'm doing with these inverse transformations is labeling this original point P prime in the post space. Now I'm going to label a lot of points in this post space and then do marching cubes, as you can see here on the right, or marching cubes or whatever you have to reconstruct the surface, and obtain this signed distance field in the post space. Okay, so you could think of like I'm in a post space and I go back to canonical space and I look up what the signed distances should be, but then I do marching cubes on the original post space. And yeah, so basically doing this, you can train the model with raw scans, and you can achieve a level of detail that is, it's quite nice, actually. This would be really almost impossible to do with meshes, or you would need very high resolution, and then you would run into problems if you have like complex clothing with different topologies and so on. So here we have like, we can, so here's the model generalizing to new poses, I should say that. Yeah, and it's producing this basically this nice dynamics with these implicit functions. We can also train it to predict the deformations of a single piece of clothing, like you can see here. And for example, also with skirts. I mean, we're not dealing with intersections here, but we could do this as post-process. But this is to illustrate that the model is general for different topologies, which is quite nice, I think. And it's also quite nice if you look at models like the simple model, it has a lot of analogies. The only thing it's formulated with an implicit representation. Also, we trained it to reproduce the simple model basically, and as a function, with an implicit function. And so we have the model as a function of pose and shape. And the advantage with respect to the simple model is that if you have the model you use the model for interaction, right? Interaction with the world, then you have the signed distance field. I mean, CU has some examples of how to use this to avoid interpenetration and so on. Yeah. So there was a recent paper called Scannimate, which turned out to be very similar. So I wanted to point out a little bit what the differences are. And this is a gross simplification, but just so that we understand a little bit. So Scannimate, in a way, what it's doing is for every new pose, is sort of learning a new signed distance field. Okay. And in contrast, what we're doing is we have a constant signed distance field, which is learned by the network, but this is constant. And then what we are learning is to displace the points, the underlying space, right, with this displacement field. So that's why we have this delta P of theta. And this brings like especially advantages to model details. And also another advantage is that we do marching cubes on the post space instead of on the unpost space. And this allows you to represent skirts and more complex clothing topologies. So if you look closely, like you will see that basically NeuroGIF produces smoother results than Scannimate, and especially at wherever you have like a little bit of sharp edges and so on, it works better. This doesn't rely so much on just skinning. Okay, so the advantages are more flexibility in terms of topologies and better detail, and it's also a simpler model. I mean, Scannimate is a great paper, right? It's really nice, but I just want to point out here the differences. Okay, yeah, so we did numerical comparisons there. Yeah, sometimes we're better, sometimes it's almost equal. I mean, no, I mean, for some data sets, we are quite better, but I think visually is where you see most improvement, especially with these details. So if you're interested in details, just add this learn deformation field and it's powerful. Okay, so we had this lack of control and meaning, and now we see that we can output as a function of pose and shape, we can output an implicit function, which is nice. And I think there's going to be more and more, right? There's still limitations with this NeuroGIF. that we need to address, like, for example, dealing with multiple clothings within the same model and things like that. Okay, I mean, you notice that this was mostly about the work done in my group, but there's a lot of exciting work happening in this space of neural implicits. Yeah, from the panelists, from Angela also, and many other people. It's really difficult to keep track. I mean, this is a really nice list. I'm not sure if Vincent keeps updating it, but at least a few months ago, it was quite nice to basically, he categorizes different approaches, and it's quite nice to keep track of what's going on. All right, and now just coming to the conclusion and bridging a little bit the gap of like how this connects with humans interacting with the world and these neural implicits. So I was showing some video of HPS. So what is HPS? So what we did is we actually, this cannot play all at the same time. Well, whatever. What we did is like we placed cameras on people, and we 3D scanned large environments, and we also equipped people with IMUs, and we let them interact with the 3D world, and we used visual localization to localize the person within the 3D world, and then we use the IMUs to obtain the pose, and then we integrated all together, like visual localization, IMU information, and 3D environment constraints to obtain like captures of real humans interacting in the world. And this is joint work with Thorsten Zadler also. And yeah, we were really happy that this was selected as a best paper finalist at CBPR. And we hope that this data set will be useful for people that want to build agents that behave like real humans. And I think the first step is to capture real humans interacting with the world accurately. Yeah, this I've shown, I will skip that. Okay, so how this all fits together. So things that I keep thinking about, research questions I keep thinking about. Okay, we know that neural implicits are flexible. And we know that like one goal of AI is like to build agents that interact with the 3D world. So can we use neural implicits to build some sort of internal map of agents that is updated as the agent interacts with the 3D world? And allows these agents to know what's around them, know where the particular room is, and then maybe get more detail for activities that require more detail and less detail for activities that require less detail, and so on and so forth. And so the question is, can we build these representations on the fly? And if so, will they be these neural implicits, or will be something else? Will be a combination of meshes? Yeah, it's exciting. There's lots of open questions, but these are some of the questions I think about. Okay, so in conclusion, like we've seen neural implicits, I hope I convinced you that they are flexible for representing multiple topologies. I hope you're also convinced that you need to decode based on intrinsic shape features, so deep features instead of point coordinates for most problems. That's what you probably want to do. I didn't have time to talk about stereo radiance fields. This is a combination of stereo with nerve in order to generalize to different scenes. It's also quite cool, I think, and you might want to check this out. So stereo radiance fields. But it's the same idea, like do not decode point coordinates, but just project to the image, extract some features, extract some sort of similarity between multiple views, and then decode, right? And then we've seen that neural unsigned distance fields allow to recover a broader class of shapes, including open surfaces. I've shown LoopREC, which can perform non-rigid registration in a self-supervised manner. And I recall that registration is the workhorse for many of the statistical models, and a lot of people have asked us, and now you have code, the more classical registration and the LoopREC registration. This code is available online, so please check it out. And yeah, we're starting to see neural implicits being more and more controllable. I have to say, still, meshes are still easier to control, I have to say, but we're making steps in this direction. Maybe my last message is, do not disregard papers from the 90s or the 2000s. And also do not disregard simple ideas, because simple ideas many times they survive test of time, right? So sometimes, oh, like this is obvious. Yeah, but it's obvious because you've seen the solution already, right? So yeah, with this, I would like to thank grant agencies and sponsors, and yeah, I'll be happy to answer questions now.
Thanks for the really cool talk. Lots of very interesting kind of new formulations and questions about how to tackle this kind of stuff now that we actually seem to be making a lot of progress in shape and 4D dynamic representations.
Mm-hmm.
So we can open up now to some questions, panel discussion. Anybody feel free to ask some stuff in the chat. Maybe I'll start with something a little bit more broad, speaking to the comparisons with different representations that you were discussing throughout the talk. So what do you think about something like simple versus a neural representation of a shape? Like you said, there's still potentially easier control over a mesh. Certainly runtime is potentially also a consideration in practical scenarios, as well as things like texturing or other kinds of downstream applications. Do you think we can replace this kind of mesh representation, or is the aim to create an improved?
Yeah, it's a great question. I think more and more, I think meshes will not disappear forever. I think more and more I'm convinced that they will not. So why is that? Because so with implicit representation, you gain some things, but you lose many other things. So for example, you lose the correspondence. You don't know where the eyes are at every instance of time. And then for texturing, like what you're mentioning, yes, you could learn a second network that predicts the correspondences, but it's an addition, right? You don't have this given. Then if you just want to animate a body without clothing, I mean, the meshes look great already. And if you put like texture, it just looks great already, looks good. And this is used in industry and for many applications is used, right? And I think it will continue to be used. But if you care about how far you are from a given object, for example, like you're dealing with interactions or you're dealing even with intersections with clothing and stuff like this, having the distance field is very useful because you immediately know, oh, what are the collisions, right? So that's definitely a clear advantage of implicit functions. And then the other clear advantage is if you want to represent things that are difficult to parameterize with a mesh, like, for example, clothing or a variety of objects, yeah, I don't think it will be represented with meshes, because how can you build a model where you have a single mesh that deforms into being a laptop or whatever, right? I mean, things that change in topology or a cap or whatever, right? So, yeah. So it will depend. And speed. I knew I was forgetting a point. Yes. Why I'm still not fully solved yet, but it might change. It's because like right now you need to query all these points, and this takes time also, right? And with a mesh, you just apply like a bunch of linear matrices to the meshes, to the vertices, and then you're done. Here you need to evaluate lots of points, and then at the end you need to do marching cubes, or you need to do this thing that I explained with the neural distance field. This is all like a little bit annoying still.
So how do we do this? We
just feel free to ask anything.
Okay. Yeah. So really cool talk. Thanks, Gerard. And many amazing works, very inspiring. So I have a question about appearance, right? So like recently there are really avatars, Scannimate, like neural GIF, and also some work from our group. And like, but none of them really have a really convincing appearance model yet, I think. Right. So
you mean appearance, you mean color?
Yes, a color, texture, this type of things, right?
Yeah.
And
but why is that?
Yeah, I'm wondering why is that, and what's
there's a clear answer, right? I mean, the reason is that none of these models predicts correspondence, and for appearance you need correspondence. You need to know that the eye here in frame number 0 is this point in frame number 100. And the current implicit models, they are kind of like, so what we write in papers, oh, it's great because now I don't need to do registration. It's true, right? It's really good. I really like it, not having to do registration. It's a pain in the ass, but we're losing also, right? Where we don't know where each point lands. And so we're losing something there. And that's why we don't have appearance also.
But about like this comment, you don't need to do registration. I'm not sure. For example, for NeuroGIF, if I understand correctly, you still need to do simple fitting.
Yeah, with registration, I mean, yes, I don't count simple fitting as registration. I count registration like as non-rigidly deforming, where all the mess. I mean, simple fitting, this is very robust. This works, but you start dealing with non-rigid deformation, and then lots of weird things can happen. This is where you really need the skill, right, to really get this. So when I mean registration, I don't mean simple fitting. Yeah.
Yes.
But it can be, right? I mean, we've seen some like animatable nerves. It's a function of pose. We had something, but it's subject specific. Yeah, it's true. Like it's still, but even simple, like it doesn't have an appearance model, right? It just shape. It just appearance is much harder. It's just it's difficult to parameterize with a mathematical function.
Yeah, thanks.
So yeah, thanks, Gerard. That was a really great talk. So just thinking back about your point about extracting deep features. So instead of having this global code, let's call it, then you have local features instead. So something I've noticed with these kind of methods is that often when you then do the full reconstruction, yes, you can learn to complete the shapes, but often you will actually have much more details in the areas that are visible, but in the other areas where you didn't actually have the data to start off with, obviously, you're not reconstructing with as much detail. And on the other hand, the methods that are using global features, let's say, they kind of do a better job of that completion. So yeah, how do you have you
yeah,
combine these two things together, and is that the way forward?
So before I answer this question, I should point out that the deep features go from global to local. So it's a multi-scale grid, right? So it goes from local features to more global. So at the end, you also have the global, and that's why you can complete shapes. I think like the global models also are not very detailed. And I think the reason is that, yeah, I mean, they are trained with L2 or L1 losses. And then if you have, for example, like you've never seen the back of a person, and you might have many different wrinkles, many different orientations, there's a lot of variation. It's a multimodal problem. And so what the networks do is they just average whatever. And the only way I could imagine to get these details is to train something more like a GAN, but then, yeah, I usually try to avoid GANs whenever possible. So, but I think this would be one way, right? It should be more like GAN based to get this more detailed thing. Then you can sample solutions from it. I think that would be one way. Yeah. Actually, we wanted to do, it was one project, but it died at some point. Yeah.
I also have another question about the last work, the neural GIF work, which is really, really, really great, I think.
Oh, thank you. Reviewers didn't think the same. It almost didn't make it. But yeah, thank you.
We know what reviewers are like, right? So I think, yeah, maybe there wasn't so much time to explain it, but it wasn't completely clear to me the amount of supervision that's actually needed. Whereas your previous work, the LoopREC, was about being able to do this unsupervised. So use the loop constraints to do the learning in an unsupervised way.
So so you could think of it as a weakly supervised method, in the sense that you don't need non-rigid registration. And so the supervision comes from the scans. You take 3D scans as input, you feed the simple model. You need the skeleton you need the corresponding pose for every scan. You need that. And then you train based on the occupancies of the scan, right? So that's the supervision you need. You take a sequence of scans, and and then you learn each of these functions: the blend weight prediction function, the displacement function, and so on. Yeah.
So how good does the data need to be? The scans. Can you work with noisy data, partial scans?
You can, and we do, but then you have noise at the output as well. So like the network learns a little bit noise patterns. So for example, we saw the scans have sometimes like the hands are kind of noisy, and the outputs of neural GIF, when they are trained on this data, they also have these kind of noise patterns. So it's not so surprising. I mean, the network has always seen these kind of hands, so it thinks, okay, that's how a human looks like. So I don't know how to go about this. Maybe you need a little bit of clean data, and then the question is like, how can you use like with clean data and then noisy data, how can I learn something that learns the actual signal? Maybe that would be one problem to formulate, right? But if you only have noisy data, I mean, you cannot expect magic, and it doesn't happen.
Yeah. I meant more, partial scans where, maybe the quality of the data is okay, but you're not seeing the complete.
The complete. Let me think. So, actually, it could work because this one is trained with signed distance, but if you train using like this NDF formulation where you deal with the unsigned distance, you could basically learn with this incomplete scan. You could learn, okay, I need to predict this unsigned distance, and then project the points with NDF kind of, and then you could train with different scans. It will be inaccurate at the boundary because for example, like if I only have half of my face, right, and the distance here, it will be larger than it should be because I don't have my mouse, but I could maybe ignore distances above some threshold to deal with incomplete data. Something like this. Would be interesting to look at how to do this well. Yeah, interesting.
Maybe a semi follow-up to this. Actually, interestingly, we've tried this a bit with the 3D scene kind of scenario, and it is very challenging because, like you say, that some of the distances are wrong when you see only partial data and you have a distance representation, and so that has to be carefully dealt with to try to filter out any kind of wrong distance. But so in terms of like shape representation and surface representation and stuff like this, of course, we care mostly about actually just the end surface as a result, not necessarily the entire density of the 3D space. What do you think? Generally the neural representations typically then define the surface throughout the entire space. And there's also traditional graphics kind of representations that take sparse approaches, maybe not as obviously a mesh as an example, but just sparse volumetric representations or other kind of representations that can then be defined or well-defined near a surface. So like an SDF can also be well-defined in these examples that you mentioned if you define it only near the surface, right? Instead of across the entire space of the 3D volume.
Yeah, that's a great direction. Hopefully you will see something coming soon.
Okay.
So there's one paper that is already out there from Christian Theobald's group, which is called Sparse Neural Voxels, and they basically they first get some sort of octree representation, and then they define the nerve only on those voxels so that you're not yeah, I mean, you're not wasting memory. Another way is to encode like an implicit function on top of a mesh, for example, right? And yeah, so it's something that we're looking at, yes, and it makes a lot of sense because then you're saving a lot of efforts and capacity and computation, and yeah. But maybe there's something even better than this that one should think about. Yeah. So actually, one thing I'm also quite interested in is like, can we represent objects as like some primitives, and then the implicit goes on top of that, right? And there were some works on this, but then it would be another way, right? Can you represent the implicit function on top of this explicit meshes? And I think for many things this would be useful, right? To have more understanding of what the shape actually is.
Yeah, I mean, that definitely seems pretty interesting. I think, so what do you think about, sorry if this is getting a little bit further away, what do you think about like the data? How much can we learn all of this stuff from the data that we have currently available? What do you think? I mean, you've done some stuff that is like weakly supervised and self-supervised, or do we need to be creating new data sets?
Yeah, so in my experience, always the process always works the same way. You first have to get your hands dirty and really dirty, do the engineering work, then get this first warm startup supervised data, and then like add more noisy data, unprocessed data on top of it, and then things work. When you just throw noisy data and labeled data to algorithms, it's really hard. It will work to show some nice images in a paper that will get accepted to CVPR. It will say, oh, like, yeah, I can predict correspondences. Yeah, I mean, I see really nice maps, but have you used them for anything practical? Because when you start using these maps or depth maps or things that you see in papers, it's not, yeah, I mean, it's not really useful then, right? When you need to do an actual problem. So I think usually, like, yes, basically the process usually for my group works like collect some data that is high quality, and then, okay, you cannot do this for all the data in the world. So then add this more noisy data, and yeah. But the problem I still see is like many times, what I see, the pattern is supervised data, you get already something, unsupervised data, you're getting better, and at some point it saturates. And then it's like really frustrating because you would think, oh, I keep adding unsupervised data and I'll get the best algorithm in the world, but that's not what I've seen, right? Many times it's like supervised, unsupervised, and then saturation. I don't know if you guys have observed this pattern, but I see this quite often.
No, generally this is the case, I think. And then there's usually then at some point there's an injection of a new paradigm. I guess maybe currently it's all this contrasted learning in order to ramp up the more unsupervised feature learning. But it's still not, you know, like the full breakthrough in terms of performance. So obviously there's always more, especially in these kinds of domains when we don't have nowhere near as much data as in some other tasks.
And also I think what is important also is like, I think in other domains like recognition and things like this, it might be more powerful. The unsupervised data might be more powerful than in our domain, where maybe we care about like getting all the details right, because then noise really hurts you, right? Whereas if you're just recognizing cats from dogs, well, it doesn't really matter. Things are a little bit misaligned or whatever. So that's my intuition also, that also for many CG applications, yeah, it's more difficult to get these unsupervised paradigms working nicely.
Yeah, speaking about data, so I have another question related to this. So it's a HPS, like this motion data collection. So I think it's a great setting to collect large-scale motion data in a large-scale 3D environment. But if we see the data quality, right, I think there is still like a gap between like data collected from such setting compared to the data we collect from motion capture lab.
Yeah, definitely.
Yes, and then like, what's your thought on this? Like, how do we bridge this gap? So do we need more sensors or cameras, or like what would? Yeah.
Yes, I mean, I think it's a really good question. I think so. One way would be to learn some initial model from this mocap-based data, or maybe with Kinect or whatever, like that is more accurate. We're also looking into this, and then integrate this model in HPS to improve further, right? So I think what HPS could do better, for example, when the person is about to sit on a chair, I don't know, for us, when we look at the videos, it's quite obvious what it should do, right? So maybe we can learn like some prior so that the agent does what we want it to do within the capture thing. It's not fully modeling, it's kind of integrating a bit of modeling within the capture process. So maybe having a little bit of a prior model learned with this more expensive equipment, and then scale it up, that would be useful. But also, I think it's useful to think in terms of what are like close range interactions and what are long range interactions, and then use different sensors and different setups for those. I think that's also useful.
Yeah, so another observation I have on this motion capture, I mean, for the closing surface, right? Now we look into detailed like deformations, right?
Right.
But if we think about human activity capture, we are still at a very coarse level in the sense, like so far people may be able to capture how humans walk on the floor, like sit on a chair. But
right.
If we go to like fine-grained granularity, for example, how human like open a book, how drink a cup, right? How do we capture data which have this four like range of different action granularity? I think it's also a challenging question.
Yeah. I mean, like with an expensive 4D scanner, you kind of get everything, but then you lose that it takes a lot of time, you get very limited subjects, you cannot scale that much. So we're also looking at something that is a bit in between. Hopefully, like this also comes out at some point, because like it would be good to think of like different capture modalities. And I think this 4D scanner, like it will be like the kind of like really the gold data where we start with, but then we need something mid-range and then something even less and less sensors. And eventually we want to use YouTube videos, right? But to get there, I think we have to be careful. I think I don't think like we're now at the stage of I just take YouTube videos and I learn really powerful interaction models from them. I think this seems like too ambitious. Maybe I'm wrong, but it looks like.
Yeah, I think so too.
I have a question about the control. You towards the end of the talk, you were adding control to your representation, and for me, this is probably the most important thing, right? Is to be able to have some parameters or a way in which you can control your representation so that you can then apply the deformations. But it seems to me that the way that you've gone about this in neural GIF is more that maybe I'm wrong, so correct me if I'm wrong.
Go ahead.
Your control parameters are either a skeleton or somehow the simple model, right? Because you're first aligning with a simple model. So right. Your controllability has been maybe learned in advance or through the simple model or you're aligning it through a skeleton. So I'm quite interested in what you think about in terms of how can you actually learn this deformable model directly in a using a neural representation. Is ultimately simple, just as you said before, it works. It's why try to learn something different if this is actually working all the time? Do you think we should, should we find a different learning approach, or does that mean that, you know, we're going to hit the wall with having to register all the meshes and solve the registration problem, and therefore, you know, it's going to be.
I think it's a great question, but I could imagine different answers. I'm not sure at which level you're asking, but let me try to answer. So definitely it's worth doing, first of all, because simple, it just only works for humans, right? And if you have a general framework that can, for example, learn the deformation modes of objects, that's more general. And also, if you just want to put some avatars in a virtual reality application, or you just create an animation in your movie, then maybe, yeah, use like a more standard model like simple. That I don't think reinventing the wheel will get you further. But if you're trying to develop an algorithm that reproduces a little bit, or attempts to reproduce how humans learn things, then it's definitely worth it. I mean, I see my son, and my son doesn't know what objects can do, right? And how can they move, and he experiments with them and keeps moving them, and then he learns, okay, this moves, these are the degrees of freedom of this object. And yeah, and this is definitely really exciting to learn this from data. There are some works, but it's much less so, that learning the deformation modes or the skeleton, it's a super hard problem, because you have combinatorics into it, right? Which I mean, if you have a part-based model, which parts depend on which other parts. And yeah, it is quite challenging, but yeah, it's definitely exciting to tackle. And also maybe at the other level, this is more like a kind of at a deeper level, maybe more less deeper level is like, well, we know what simple cannot do, right? So for example, cannot do clothing, it cannot do many things, and for those it definitely makes sense to learn other deformation modes. I mean, in a way, we're learning the deformation modes of the clothing are learned from the network directly, right? There is no, it's modulated by simple if you want, but it's kind of learning new things, right? How skirts deform, for example. Yeah.
Awesome. Well, I think we're probably close to running out of time. If there's like one more question or anything else?
I have one more question. So, I mean, what you've shown us is, I mean, it's truly awesome. But you know, the inputs are of what you've shown us are 3D. So yeah, I'd like to hear, you know, a little bit more about what about if you have images as inputs, and are you also working in this direction?
Yeah.
What's maybe coming our way?
Yes, definitely. So just very quickly, so you might want to check, for example, this paper, stereo variance fields. I'm trying to find the slide that summarizes the idea. You can still see my my slides, right?
Yeah.
So this is basically like generalizing nerve to different scenes, and you have multiple views. And now, instead of sending the point to a neural network that will predict the radiance, what we do is we take this point, we project it to each of the images, and then we have a neural network that basically combines the features seen in all these different images. Mm-hmm. And the idea is, this is inspired by stereo, and what we're hoping is that the network learns to see which features match and which not, which you know, at the pixel level. And yeah, and then like basically you're learning some sort of a bank of similarity functions. And this is really cool, because then you can generalize to new scenes instead of memorizing, right? And for example, this is results on a new scene, which was not seen before. Let me play this. And yeah, it can produce quite nice results. And basically this is also only trained with 10 images instead of like these 100 images that were used in NERF. So it's quite nice. And then you can basically, because you have this model, you can overfit it a little bit. You can fine tune it quickly in 5 or 10 minutes to the input data. So this is just one example, but yes, we're also definitely looking at having images as input. Yeah, also with humans and so on. And yeah, hopefully more things come up in the following months.
That's great.
Okay, yeah, thanks again, Gerard, for a really cool talk, and thanks, Lourdes and Sue, for a really interesting panel discussion. All right, so I think that's all for today, and then see you guys next time.
Yeah, thank you very much again, everyone. Yeah.